of our recent work on stretchable soft sensors that could be used for sensing force, although not so much, I guess, touch in the sense that this conference is considering touch. And we also use these sensors for health monitoring and so on, which I will go over. Majority of this work done it was done by my former PhD student, Michael. So I would like to acknowledge this at the beginning of my presentation. So he's done a good job. So why do we care about sensing force? I think I approached this problem from a completely different perspective than pretty much everybody else, I would say, at this conference. Initially, we were just trying to develop a wearable system for detecting breathing in animals, and especially working dogs. And it's because they have a furry skin and so on, we cannot use conventional methods for measuring the vitals of animals. And so we started this whole project really by just trying to develop a force sensor that would be strapped around the chest of the dog, and then we would measure the expansion of the chest using our, in essence, strain gauge. And then from this, we would try to identify breathing patterns that would be associated with various health issues. And one of my collaborators and good colleagues from the North Carolina State University, Alper Boskurt, he told me that a good PhD creates hundreds of jobs, but most PhDs create only one job, and that's for the next PhD student. So I think with this project, we are a little bit ahead of a typical PhD, but still behind, because I think that it already created two jobs. So, and we developed essentially a respiration sensor, which I will go over how we did. And this could be basically produced in the form of a belt that could be worn over the chest, and then monitor the expansion of the chest. And obviously the same technology could also be integrated and then into various, or I guess created in various other forms to measure gripping force, which could be important for upper limb rehabilitation, among other things. So, and I will go over, how we have developed this technology and where we are right now. So, but what you're seeing right now is that the user is squeezing a rubbery ball, which we can sense in real time, the gripping force. So the way we created these materials, these force-sensitive materials, is by using a conductive stretchable polymer, which we have produced in the lab. And it's just a simple composite of carbon black, so conductive carbon particles, and silicone polymers, so silicone elastomers. And these materials are fairly well known in the materials community for sensing touch. So these are conductive polymers essentially. But one of the reasons why we chose silicone rubbers to create the force-sensitive material is that because silicone rubbers are biocompatible materials, and then they're fairly inexpensive. The mechanical properties of these rubbers are highly tunable. There are so many different formulations, and obviously, one can also make custom formulations. And then they are very durable. So we can easily take the silicone rubbers and then add conductive fillers inside to create force sensors. And depending on how much filler we add, we can even produce stretchable conductors and so on. And silicones are very chemically inert. In fact, this is one of the reasons why they are the preferred material for, let's say, breast implants, among various other implants. But this is when creating devices, chemical inertness, becomes a bit of an issue, that's why it's highlighted here, which we will talk about. But the way these sensors are created are fairly straightforward. Essentially, we just take a silicone formulation. In this case, it's PDMS. and then we mix it with a carbon black particles, and then this becomes an ink, and then this could be printed on a stretchable substrate. And once the ink cures, because this is the prepolymer, so it still needs to cure to become the final stretchable material, and then it's kind of ready to use. And the material itself, once printed, it looks something like this. So the PDMS is transparent, so that's why you cannot really see, but it's printed on a piece of elastomer, this conductive stretchable material. And it's incredibly thin in this case. It's I think about something in the range of 50 microns, if I don't remember, if I remember correctly. So, but the chemical inertness is really an issue with these materials. And if you go back to the academic literature, it's very easy to see that people have been making these materials for a long time. And when we started working with them as well, it became incredibly obvious that there's a big issue with these materials. As a force sensitive material, it seems to work well. However, we cannot reliably connect it to electronics. And when we thought about this issue a little bit, and it also became obvious why these materials are not out there. Why don't we have them everywhere? Because they're cheap and quite sensitive and so on. So it became obvious that because when Michael started working on this idea, we thought we basically just take this idea forward and do a more like a systems related project where we would develop these sensors and then put them on dogs and then make measurements. But we had to do chemistry. That's what we ended up doing. So, and the reason why, again, we cannot see these materials out there is the problem with the contacts. So, what's commonly used in the literature, and I call this the contact problem, is people make these composite sensors and then attach the outside electronics with a silver epoxy conductive adhesive. So the problem is that silicones are very inert, so they do not really react with the adhesive. And when we apply force, for example, in this case tension, we see that the adhesive starts cracking, and the electrical contact really breaks between the sensing layer and the outside electronics. And even if it doesn't break fully, sometimes the mechanical fragility of the adhesive basically adds a lot of error to the measurements, and we obviously do not want this if we want to use this as a sensor. So and the solution that we have developed has completely eliminated this, and which I will talk about today. And what it really is a material that consists of copper and porous silicon, which can be covalently attached to the silicone-based material. And the way it kind of works is that we decided to explore a method where we don't really change the chemistry. So we're all using silicone-based chemistries to attach things together, and because they are very similar materials, they attach each other covalently. And well, honestly, it's like the same material more or less. They attach each other covalently, and the bonding is very, very strong. So, for those of you that are not too familiar, I will use two terms that are very similar and often mixed. So silicones are the rubbery polymers, and silicon is the element that's the semiconductor used for making chips and so on. So and these two terms are quite important, especially in this study. So the way kind of our contact works is that it's a silicon. We take a silicon wafer, and then we create a nanostructured surface on one side, and then which we can then use for electroplating copper. And then and because copper is very easy to solder, and then we can basically bond the other side of the silicon wafer or the silicon piece on the silicon layer, and then the other side can be just soldered onto an electrical wire. And the good thing about this is that because silicons are highly heat resistive, in fact, this is one of the reasons. So if you buy baking paper, for example, it feels a bit like oily, greasy. But in fact, what it is that it's just paper that's infused with silicone rubbers. Silicone rubbers are highly temperature resistant, so they won't decompose easily. So we can easily basically solder electrical wires onto these contacts. And obviously, it's more the material science side of it, which is not super important for this conference. But essentially, when we nanostructure the surface, when we electroplate, because without nanostructuring, the silicon, the copper layer just basically peels off on its own. And but once we nanostructure the surface through a chemical process, then we can create interlocking structures within the substrate or underneath the surface, and then the material or the contact becomes incredibly robust. And we do plasma bonding to attach the copper to attach the silicon wafer on the silicon rubber. So we just basically do oxygen plasma and then literally just attach them together, and then they're bonded and covalent bonds are formed. So this is called the condensation reaction. Again, it's not too important. So, but all you need to know is that it's a very robust contact. So the figure on the left shows the strain stress curves, where we basically we attach wires on both ends of the sensor, one with the copper porous silicon composite contact, and the other one is just with silver epoxy. And then when we stretch it, when we stretch these materials, the silver epoxy essentially cannot withstand high strains. But not only that, it actually starts really breaking. So even if you think that you're getting a correct result, below 20%, it's not really working. And then this is also obvious when we look at the variability of the measurements, the resistance measurements. So because at the end of the day, these are just resistive sensors. We're just measuring the resistance of these conductive materials, which change with strain. And then when we stretch these materials, we also see that the copper, the silver epoxy gives very high variabilities as we stretch them, and it's purely because the material is just cracking beyond some 15% strain. And when we look at when we investigated the material junction microscopically, we see that the contact between the copper silicon composite contact and the underlying silicon elastomer is so strong that actually the elastomer itself fails first before the contact. And we really like this because it shows that the material itself will catastrophically fail when it goes beyond the limits of operation, and not just fail a little bit and give a wrong result. So catastrophic failure in this case is a good thing, especially if you want to use it for biomedical applications and so on. I mean, actually for any application, for any sensing application, it's not a good idea to have erroneous results. And when we cycle these materials, we also see that after 15% actually strain, the silver epoxy contact fails, and the copper porous silicon contact does not fail essentially all the way up to 30% strain, and then cyclic loading. And then when it fails, it just fails completely. So I'm not gonna spend too much time on this, but because we have a semiconductor and we have metals and so on, the junction is relatively complicated. So, and it works as a Schottky diode, along with there are some capacitive elements. So proper basically signals need to be applied to operate these devices. But what really this whole technology allows us to do is then monolithically integrate everything into a single device. So, for example, this is the sphere or the ball that I showed you earlier on with that video. And so what you see here is that it's a silicone ball, and then inside we have a silicone-based material that's used as the sensor, and we also have silicone contacts. But what happens that all these materials react together, and then we have a very monolithically integrated, a single-piece device. For example, if we were to put in just a PCB-based or a thin film-based sensor that's not made of silicones inside this ball, then actually it would kind of move because it wouldn't really bond with the silicone rubber. So and here we have a really solid piece that's it just acts as a single monolithic device. So the we can do some time resolved grip measurements, and then so by changing the grip force, we can easily see that the signal increases, and then we can go faster, slower grip or squeezes, and we can resolve all of these things. And then our signal is not super clean, and one of the reasons is that we operated here our sensor with a DC signal, so we are susceptible to these capacitive effects and drifts, which we have later on fixed. So, but something really interesting happened, and not so long ago, we actually found out that there is a new manufacturer that's producing the conductive silicone rubbers, so we were able to get some samples from them and then try it out with our method, and it works beautifully as well. So this way, we no longer need to synthesize our own rubbers, and we can just buy them from a commercial supplier. And this is quite important for translation, because whoever is taking over this technology, they may not be a chemistry company, so they may not really have the facilities to really synthesize these materials. So and so we can take these commercially available rubbers and then attach our contacts on them, and then we can really cast them into any different shape. So we can make cylinders out of them. We can make devices that look like a pen. For example, if it's for upper limb rehabilitation of children, we can make them small. We can make them big. So this method is very highly flexible, and that's one of the things that actually attracted the attention of the healthcare professionals, because in comparison to the hard devices that they're using, they think that if we can make a similar thing to what they typically use, which is a putty, a soft device, and then we make it smart in a way, and that way we can kind of monitor the rehabilitation itself. Would be really, really useful for them. So and we can twist these materials. So this is the cylinder, and then we can bend, we can stretch, and we can basically measure all of these forces with our force sensor. And by changing as I mentioned, the mechanical properties are quite tunable. So by changing the silicone formulation, for example, going from a hard silicone to soft silicone, we can actually change the characteristics of the device itself, and that would allow us to basically make a device that's harder to squeeze or softer to squeeze, or sense also forces with different sensitivities and so on, and that adds a lot of flexibility to design. So
question already.
Sorry, there's a question.
Not that we are already in the questions, just that you know. So you have only 4 minutes left. Yeah.
Okay, cool. I'm just wrapping it up now. So yeah, this is the twisting demo. Which we can capture. Okay, I'm gonna go forward. So obviously we can also gamify rehabilitation using these devices, which I will also briefly share. So by squeezing essentially the device itself, we can manipulate the balloon itself to collect stars, which we can track. Okay, I'm wrapping it up now. So in conclusion, stretchable conductive composite force sensors are geometrically scalable and they're quite versatile. So we can capture the full range of motion because it's a rubber, and then they could be monolithically integrated. So they are highly reliable because of our contact technology, and there's really lots of potential for digital rehabilitation. I'd like to thank my sponsors, especially also the organizers who put this entire event together, Mohsen and Tapamayuk. I don't know if there are other people as well, but these are the people that have been in touch with me mainly. And I'd like to thank my team who've done the work, really. And I'd like to thank my collaborator as well, Mike Mace, mainly from Grippable, who helped us out with the gamification part. Thank you very much. I'm so sorry that I went over. I think I timed myself poorly.
Thank you very much, Firat. So does it have any questions? So if you have a question, you can raise a hand. Okay, so I have already one question. So the sensors you have presented are pressure or force sensors. Do you plan or are you working on totally different kind of sensors, for example, to detect chemical reaction or to detect, I don't know, radioactivity or, yeah.
Absolutely. So this could be done. And in fact, we do a lot of like chemical sensing. But we haven't like done it with this kind of technology, but it's completely doable, especially like doing some electrochemistry based sensing, because we already have a carbon based material which we produced, which is inert, and then this could be definitely turned into a kind of like chemically sensitive sensor, and for measuring various analytes, obviously. Which would be, chemical sensing is very, very tough. So it would really require a specific application, and the sensor would need to be developed for that application.
Okay. Thank you very much. Any other question? Mohsen?
I don't have a question now, but if there would be any question, please contact Firat directly, and I'm sure he will answer your question.
Yeah, so you can, so Firat has a well-designed website. You can contact him.
Thank you very much for having me.
Thank you very much, Firat.
All right, have a good day.
Thank you very much.
Yeah.